So I'm going to be talking about some farm systems modelling that's being used to look at the management effects and trade-offs between carbon and nitrogen in that lucerne system. So the aim of this study was, in the first step, a validation of APSON's water, carbon and nitrogen processes with the irrigated and non-irrigated paddock-scale lucerne experiment at Ashley Dean, looking at the productivity, the water, the carbon balance and the nitrogen leaching, and then do some simulation modelling to ask questions about what happens if you change those management levers. So this is just one application of the data. I think there's a lot of other things that could be done with it as well, but I mean, I think this is quite a unique opportunity to robustly test a model. To my knowledge, APSON has not been tested to this level previously. It hasn't had such an extensive data set put against it. Often it's only annual crops and annual experiments, so this is a really fantastic opportunity. And models, I'd like to also make the point that models are a really good way of testing scenarios that we couldn't possibly do experimentally. It's really hard to run every weather condition, every management interaction, so it's a way of kind of exploring the system. So, as I said before, Scott gave a really nice introduction. I won't go over that again. But the period we looked at was the midpoint in 2016 to the midpoint in 2019, which gave us 3 continuous years of data, and the spin-up which was excluded. Beyond that, then, we used the productivity data, the water balance data, the nitrogen leaching, and the carbon fluxes within the system. So for those of you who aren't familiar with APSON, I'm guessing a lot of people are, but just in case you're not, APSON is a farm systems modelling framework developed originally out of CSIRO, Queensland Department of Primary Industries, and the University of Queensland. Now has a much larger consortia. I think I should have updated that because I think there's some new people in there as well. So there's University of Colorado in there as well. So, but it's a large consortium of organisations contributing, as well as plant and food. Within that framework, there's a mechanistic process-based models, and those models interact to form a farm systems. As I said, it's a global research effort. There's a science review process to get material and models and code into it, and also software standards are maintained and improved, hopefully. So, as I was saying, it's a framework within which we have a central engine around which there's a number of modules that can be bolted together. In this case, we used SAW-WAT, which is a tipping bucket soil water model. We used soil nitrogen, which is inherited from the series models, so organic matter. We also used the lucerne part of ag pasture. I believe there's a new lucerne model coming, but in collaboration with Derek Moot, but it's not there yet. So we used an existing one, which is part of ag pasture, developed by Ag Research. So how well did the model perform? So looking at standing biomass over the 3 years, generally above ground biomass for both the irrigated at the top panel and non-irrigated at the lower panel performed reasonably well. We're able to reproduce the seasonal dynamics. There's some questions around whether it gets quite right the spring rapid growth and the autumn remobilization processes, but generally we get a pretty good performance to the data. In terms of biomass removed from the system, again the top panel being the irrigated and the bottom panel being non-irrigated from 2017, 18, 19 across. Cumulative dry matter harvested from the system adhered to what was observed in the field, or managed in the field. Moving on to the water balance, with the red points being the data, the black lines being the model. Again, similar format, and the panels going from left to right go from the surface down the soil profile to 1.5 metres. And generally through and I appreciate we've squished in each one of those 3 years, so it's pretty tight in there. But generally we get a good adherence of the model to the observed data in terms of soil water content. When we look at the behaviour and drainage, Again, the red being the data, the black line being the model. Cumulative drainage over each one of those years for both the irrigated and non-irrigated was reasonably good. There's a few areas where the timing might not have been quite right, but generally speaking, this is good given how variable drainage can be. This is a pretty good adherence to the data. And in terms of leaching, again, not seeing a lot of leaching in the unirrigated, as Scott spoke to this morning, but for the unirrigated, that large leaching event mid-2018, the summer of 2018. Again, the timing, some of the timings are not quite right, but generally we're getting the right overall behaviour. And then lastly, going on to the carbon balance, this is looking at cumulative GPP. Again, top irrigated, lower non-irrigated, with the red being the data and the black being the model. And generally, we're getting it reasonably right, correct? The only place we substantially diverge is this lower panel here, and that will become important in a moment. The non-irrigated in the 2018-2019 season. But generally speaking, it's getting the GPP reasonably correct. And then looking at total ecosystem respiration. So again, the model is doing reasonably well over multiple years, and in both of those treatments. Again, we get a small divergence here, and this becomes important when I show the last slide. So when we look at net ecosystem carbon balance, now Scott talked about what that was this morning. So the red line is his data. The black again is the model. And generally speaking, once we combine all those components of the carbon together, we start to see where it's not quite got the timing right. But generally speaking, we get a reasonably good adherence. Where it does diverge more than just a little, obviously, is in this year here, and this is something we're working through. That might be that the model isn't capturing processes that are going on in the field. It might be that it's something we haven't captured properly. But for me, it's quite exciting when it doesn't work, because it raises an opportunity to ask why not. Where is our understanding not working? I'm sorry, I can't hear.
No, sorry, I'll come back to that.
Okay, thank you. Okay, so going on to the simulation modelling. So this was then an opportunity to model the trade-offs in carbon balance and nitrogen losses in response to changing irrigation, in response to changing effluent management, and in response to herbage management. And these were the three levers that we decided to look at for this presentation. We did that by asking, well, if you change irrigation, and I'm defining GMP irrigation as deficit irrigation. We all know that if you can inappropriately irrigate a system, and you can leach a lot out, so I didn't think that was worth exploring. I've done work in the past, and it doesn't really it isn't the most sensible thing to do. So we've defined GMP irrigation as deficit irrigation in this system, and that's something that can be explored further. What if the concentration of the effluent changed? So if there was greater nitrogen and organic matter within that effluent, and also the proportion of grazed and cut and carry in the system. So we looked, looked to an existing example of a similar analysis, and we're very fortunate Miko's in the room today. Hi, Miko. We did a really nice piece of work a few years ago, looking at the trade-offs between milk production and soil organic carbon storage, and this provided a really nice way of undertaking a simulation analysis to look at those management levers and the sort of thing we were wanting to do. So it was nice to have an existing sort of methodology out there. So defining the simulations, so you started by defining a base simulation for the system. So we chose the irrigated lucerne system and defined the average behaviour of it. We also did this for the unirrigated, but the results aren't shown today for simplicity, but the messages are fairly similar. So for the irrigated system, harvest was on average, and I appreciate that there was a high variability around that, but we had to pick a number. On average, around 2.5 tons of above ground dry matter, and the residual was approximately 3/4 of a ton. Irrigation during the irrigation season was approximately every 2 days, 3.5 mil. Now there was some variation in that, and quite a big variation in that. So that's something that we can explore further, but generally it doesn't change the messages coming out of the work. There was regular effluent applications, as Scott spoke to earlier, and also it was either cut and carry or grazed in situ. So, as I said, the three management levers we were looking for were irrigation, and as I said, we're looking at good management irrigation, good management practice irrigation, so deficit, and whether there was more applied or less applied. And the second being the concentration of effluent, and the last being how much, when there was a harvest event, was that all cut and carry, was it all grazed, or somewhere in between, so different proportions, and that it was able to move it from a binary cut and carry or grazed to some levels in between. You'll see the results in a minute. The simulations were run for 20 different years, and that allowed us to capture some of the interannual variability in weather patterns, and as Scott showed, there were different outcomes in different years depending on the weather. And then we looked at the average change in production, leaching, and net ecosystem carbon balance compared to the Ashley Dean irrigated treatment. So that base simulation as I defined above. So that was the process. And I appreciate this is skirting over a lot of detail, which I can't go into, otherwise we would be here all day, but something I'm very happy to talk with people who are interested afterwards. So to visualize the results, and I'm going to go through this because sometimes these, I find that they're not entirely intuitive, but once you get the hang of what they're trying to show, then they can be a useful tool. And again, I wanted to acknowledge Miko and colleagues' work there. So there's on the two panels. On the x-axis, we have the change in harvested dry matter, and it's the change from that base scenario. So what's going on currently in the irrigated treatment of Ashley Dean. And on the y-axis, on the left-hand panel, we have the change in nitrate leached annually, and then also the change in net ecosystem carbon balance for the year. So, generally speaking, if the system has lower production than that base simulation, but greater leaching, it would be in the top left-hand quadrant. Same for greater net ecosystem carbon balance. If the outcome was greater leaching, but also greater production, it would be in the top right-hand quadrant. Same greater net ecosystem carbon balance. You get where this is going, but it's useful to... after presenting this a couple of times, I knew it's really important to step through this. So, in the same way, if there's lower production on the left-hand side, but then also lower leaching below that dotted line, it would be or lower net ecosystem carbon balance, it would be in the lower left-hand quadrant. And finally, as you can imagine, if you have greater production and lower net ecosystem carbon balance or lower leaching, it would be in the bottom right-hand quadrant. So, just to give you an example of how that looks. So, what are some of the results? Well, what happens if the irrigation amount is changed? So, as you can see here, I'm sorry, I just realised that people can't see me pointing with my hand. So if we thank you, as we see where the intersecting broken lines are here and here, that is sort of our base scenario, the irrigated Ashley Dean, and then the other points are the other different levels of irrigation. And just to talk through it, if on the left-hand panel, if you're moving to the right, it's more irrigation. If you go to the left, you've got less irrigation, all the way up to no irrigation in the top left-hand corner, just to make that really explicit. Again, with more irrigation down in the bottom right-hand corner, less irrigation going to the left of that, up to the left of that, and then no irrigation at the top there. So generally the results show that for nitrate leaching, and I do recognise that if we look at the scale on the left-hand side here, this is a relatively negligible amount, but we're seeing lower leaching if you irrigate less, but also lower production. Sorry, greater leaching if you irrigate less, but lower production. If you have greater irrigation, and this is because it's a reasonable amount of irrigation already going on, it's you can follow the pattern, but as you might imagine, it would extend that way, that if you had greater irrigation, you would start leaching more. In terms of net ecosystem carbon balance, again on that x-axis, you see that we're same as before. Less irrigation, you're seeing lower production, as you might imagine. It's a system heavily reliant on water. But you also see that reducing irrigation increases your net ecosystem carbon balance and moves it up to the top left-hand of that figure. So in terms of the concentration of nitrogen in the effluent, we see here that, again, the Ashley Dean is that point where those two broken lines intersect. Less nitrogen goes down and towards no effluent, and then more nitrogen, and there was an awful lot, but just shows the range that might be delivered. Again, in the net ecosystem carbon balance, less nitrogen to no effluent, and more nitrogen up to quite a lot being applied. And as we see, as we see here, no pressure, sorry. As we see here, there's when you reduce the amount of effluent, there's a yield penalty in both of those figures on the x-axis, but on the left-hand axis, increasing effluent has a modest increase in yield, but then just increases leaching and just keeps on leaching. On the right-hand figure, a similar outcome, that as you reduce productivity, you have greater net ecosystem carbon balance. This is going up to the left. But if you start increasing effluent, there's that kind of inflection point and it starts increasing. And because the effluent comes with organic matter in it, we start to see a more positive net ecosystem carbon balance without any production benefits. So the last scenario, that last lever, was the proportion of biomass grazed versus cut and carry. And again, Ashley Dean sits here in the middle. And this was a difficult one because we chose essentially half and half. We said, well, of that harvest event, half of it was cut and carry, and half of it was grazed. And we can see here that as you increase grazing in the left-hand panel, that's up to grazing only, more cut and carry to full cut and carry only. And I'll put those same labels onto the same figure on the right. And we can see there's a negative relationship with leaching, as you might imagine. When there's more grazing, you tend to see a modest increase in leaching. But there's also a production penalty, and as you imagine with grazing, you get some trampling as well, so you're starting off from a different point slightly. If you go to cut and carry, there's a production benefit, but also a reduction in leaching because there isn't animals and dung and urine going on. And I do recognise that once you export that organic material, something has to happen with the dung and urine if it's fed off on a feed pad or something, but that's not captured here. And if you were looking at the whole farm system situation, you might imagine that you'd have to deal with that. On the right-hand side, we see a similar pattern that as you move towards grazing, you see an increase in net ecosystem carbon balance, and that's because we've got, as Scott talked earlier about, that there was more dung going back in, and more carbon was kept in the system through the trampling. If you move to cut and carry, we then see a change from that base scenario more into the negative. So just starting to bring that all together. And I wanted to put this up because I know all of those figures had different scales to make them appropriate, so it's nice to be able to put these three in context. And just briefly talk through those. So same schema, just those lines. The blue being the irrigation, and as I said, it's good management practice irrigation. I recognise that if we were using, and it's exceptionally good because the model knows everything about it. If it was poor management, you might see that increasing the irrigation would then start to pick up the amount of leaching. The pink is the effluent, and the green is the grazing. So looking at those trade-offs, and I just wanted to start to pick this apart. If a manager was looking to increase production, but also looking to potentially not increase their leaching, they might look to the bottom right-hand quadrant of that figure, as shown in green, and that would be moving over to cut and carry. So, but again, recognise that something has to be that effluent does have to be dealt with at some point. So. But then if we follow that over to the impact on net ecosystem carbon balance, we also see that that cut and carry system moves the net ecosystem carbon balance into the negative. So there is that trade-off there in terms of the carbon. But if you look at it the other way around and say, well, we're looking to not have production impact, but also increase our carbon, you might want to look at applying more effluent or greater concentration. But then that has that high concentration. But conversely, in terms of nitrogen, then that increases leaching. And you can see in these two figures that the effluent has sort of the biggest lever in terms of leaching, and I appreciate that we've chosen quite high values. So you could say that it might be smaller, but the effluent in this system, the effluent has the biggest lever, but when we're talking about the net ecosystem carbon balance and the annual one, it's the irrigation that's predominantly driving that. So just to sum up what the take-home messages, we looked at the system-level trade-offs between production, nitrate leaching, and net ecosystem carbon balance. For irrigation, more irrigation has large production benefits in the system because ultimately it's limited by water, and so therefore it's not surprising. Good management practice irrigation can have little impact on nitrate leaching. Now I realise this is a model and it's very well managed, and relaxing that could have different outcomes there, so that comes with a big health warning. But there's also a substantial negative impact on net ecosystem carbon balance, and that's as shown with the data. The effluent, greater effluent concentration has some production benefits, but in the system it's largely not limited by nitrogen. It's a legume. It's not really not limited, as I say, by nitrogen. But effluent also brings organic carbon and nitrogen into the system. And beyond modest inputs, it results in greater net ecosystem carbon balance, but also greater leaching. And in the grazing versus cut and carry, there are a modest negative impact on grazing on dry matter production because of that trampling effect. This resulted in modest increases in leaching through urine, while cut and carry decreased leaching. Excuse me. But grazing also kept more carbon in the system through dung and trampling and increased net ecosystem carbon balance. So I'm going to stop there because I don't know what the time is. Thank you. The question was, this system is very leaky, has lots of stones, and could you use the model to explore the sensitivity to hydraulic conductivity? Have I understood you correctly? Yep. So you could do that, absolutely. It does have the concept of hydraulic conductivity in there, and you could use, you could do a sensitivity analysis around that. We've actually doing something similar at the moment, so happy to have a chat with you afterwards. But yes, you absolutely could do that. You might also look to other soil water models if you're really focusing on the soil water processes. I mean, the work that Scott did with Hydrus, it's a lot more detailed. I mean, this is a tipping bucket model, so it works well in a gross way, but if you're wanting to get really finely into the detail, I don't know if Scott, if you want to make any comments, but it depends on exactly how detailed you wanted to get, I think would be my answer. Would you like to expand on that? I can step away. Okay, thank you. Yeah, absolutely. Absolutely.
I'd like to make a comment. I stand over here. Not a question.
Oh.
I just want to really underline what a great thing you've done. This is what we're aiming at really all the way through. Was that collecting data in the field and knowing about the mechanisms, but actually being able to bring those together to do some simulation. It's all about taking science and saying how can we use that science in order to inform the manager, really, isn't it? And I think you did an outstanding job, and really we look forward to saying how you can put this together to actually bring out all those different opportunities. But yeah, it's a very good sort of top of the pyramid of the program, really, and yeah, I think a great job. Thank you.
Thank you, David. I mean, it is one tool in that toolbox. I think there's other really great messages that don't need modelling, but thank you. It's been a fantastic opportunity to really test the model with such such an intensively sampled data set. So, yep, absolutely. Thank you.
I'm loath to ask another question because it just seems so great to finish on such a high note.
No.
Typical of David, really. But, there is maybe time for one more question if anybody's got one. I had a quick one. I'm sorry if I missed something.
No.
Just in relation to the leaching and the irrigation, you said you ran it with good practice.
Yes.
Deficit irrigation. Yep. Does the model capture the bad end of things if you really go off the scales with irrigation? Does the model sort of capture that pretty well? Or?
That's a good question. Yes, absolutely it would. If you were to start putting on, I don't know, 15 millimetres every day, or regardless of the weather, regardless of whether the soil was already full or even saturated, it would capture that. There is limits, of course, of how under which these models have been tested. So I don't know if anybody's done that experiment to then make sure it behaves in the same way. But yeah, it would certainly capture inappropriate practice up to a certain amount, which would be realistic. Yeah. But that's a good question, actually.